Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.
Thank you, Fred, for that delightful introduction, and thank you, everyone, for coming. This is actually, it's a privilege and a pleasure to be here. I remember X years ago when I sat somewhere back there as an incoming graduate student, and I saw a couple of these lectures, and they really inspired me to start and then later to finish the degree. But today, I guess, what I want to do is tackle just a couple of questions. So. How do we want to do this? I want to start simple and let the complexity emerge. And I guess a simple question that I can ask is actually one that my girlfriend asked, and she said, "Well, what are the applications of cosmology? Like, why do we do it? What's the purpose of this?" And I hope that over the next 2 weeks, some kind of answer for you will emerge. But the first question that I want to start with today is there an edge to the universe? Is there a size to it? So I've been thinking about how we see ourselves and how humans have always seen themselves and what the context is of our existence. And unfortunately, I dive into these overly philosophical meanderings every once in a while. But from this Mesopotamian drawing, this imagining of a Mesopotamian universe, we see a vision of the physical cosmos, the part with the stars beyond, as bounded, and the unknown heavens are left to the imagination. And then we've pierced the veil later on. This is a drawing from, I believe, the 18th century, an unknown artist, but is compiled in a French compilation. And as we pierced the veil, we saw more light. And today, we can see and we can make out the rim, the edge of our Milky Way galaxy. So this is us looking outside, right? And we can count the stars in that galaxy, in our galaxy, and we can see that it has a shape and it appears to have a bounding, but does it really? So as we look harder, we look through these edges and we see one edge after another, but is there really an edge to the universe? That's the first question. No? Okay. Let's see. Okay. So let's replace this actual observation from Herschel long ago with a more generic version of space-time. So a grid, a flat universe. Let's imagine that this is what our universe looks like, and this is just a local patch for pretend whoever said that, this is a local patch, this is not the full universe, whoever said that, okay. And so here the space is Euclidean, and so triangles have angles that add up to 180 degrees, and light rays that start parallel always remain parallel. But what happens to space-time if we put stuff in it? So remember that first part, the first Matrix movie, well, I consider it the only Matrix movie, at the end where Neo stands there and he goes, "Oh," and he bends the Matrix. That's what mass does to space. That's what matter does to space, and it does that while space is telling matter how to move, as we learned from Einstein. So without even thinking, matter flexes and bends space, locally but also globally. So there's a little bit of difference here just to clarify any little nuances. Local space can be bent by an incredible amount by incredibly dense mass to create a black hole, right? Some kind of a rip in space-time. But that's not what I'm talking about here. That's not what I'll talk about today. What I'll talk about today is all of the mass in the universe bending all of space back onto itself. Now, what could make space flat? Or how would we achieve a flat space? How would we make sure that space remains Euclidean and light rays remain parallel? Well, if space were flat, then we require that the average density of the universe to be about 10 to the minus 29 grams per centimeter cubed. Remember that a drop of water, is 1 gram per centimeter cubed. And this sounds awfully empty, but that's all the mass that it would take to avoid some kind of curvature in the universe. And so what I mean by this is that if all of this rho matter here, this on the third line here, if this rho matter is equal to rho crit, then this omega matter, this fraction of matter in the universe, is equal to 1. So then the matter density balances the critical density, and we have flat space. Right? But is this our universe? Deviations from this imply curvature, and that's what this omega k is. So if we were to deviate from this, then if we were to find deviations from this, then we could find some kind of curvature in the universe. And what do I mean by this? Perhaps imagine not just flat space, but many different kinds of curvature, from a Mobius strip to a Klein bottle to a donut like you had moments ago. I'm kind of hungry again. But let's take it a little bit more simply. So if space is very overdense, let's just think of a sphere. Maybe it's a sphere in 3 space. Then let's think about what would happen actually physically. This is a map here of the Hubble Ultra Deep Field. It's a very, very deep field taken by the Hubble Space Telescope, and I've put our little asteroid space fighter there in the middle. And what will happen is light rays that start at one point could eventually come back to the same point. Okay? That's what would happen in a closed universe, in a topologically closed universe. In a topologically open universe that looks like a saddle, if you want to, afterwards, if you want to come and touch and play with this little guy later, you can. I don't know if it'll do any good, but you'll see that parallel light rays diverge and that this little asteroids guy will go off forever and he will never come back. So hopefully what I've proven to you so far is that content equals geometry, content equals topology. So what's in the universe shapes it. But what's more interesting for us, perhaps, is what our eventual fate is. So can we use this equation to think about what the fate of the universe is? And I think there is some speculation, I'm not sure if it's true or not, but that this poem from Robert Frost was inspired by an astronomer who was wondering whether the universe would end in fire or in ice, in a crunch or with a whimper. But first, let's do a quick recap. So we have to start at the beginning so we know where we get. So we know where we are when we're at the end. Okay? So, brief history of the universe. Big Bang. Okay? That's how everything started. The seeds of a big expansion. Space and matter flying off. If you want more details, I will refer you to Tim McKay's Saturday Morning Physics in 2005. And so what does this mean? What is the expansion of space? Well, Einstein told us about how space-time is bent, and he'll also be our little model here. So we have Einie on the board here, and I'm just going to expand the space around him. See if I can do this without killing myself or making you too sick.
It's a cool laser.
I think it is a cool laser. And so if I walk all the way up here, we can see the space has expanded many, many, many times over and over again, while Einstein has remained the same size. Oh, and this would be the universe ending, by the way. Okay. So let's see a quick animation of that. So any of these spaces could continue to expand. It doesn't have to be flat. All right. And so what this means, let's get a little mathematical. Let's put some figures here. What you're looking at here is the relative size of the universe as a function of time. Okay? So back into the past, 10 billion years ago, the universe was incredibly small. Now it has some size 1. That's the size relative to today is 1. And into the future, these are our options for the size of the universe. So if it ends in a whimper and in ice, the idea is that the size will increase forever. And if it's flat, it will increase forever, but it will decelerate in its expansion. And if it crunches, then it will become 0 again in size. And these are fun equations actually that are not too hard to solve with given a few assumptions that are fun to do at the pub on an afternoon. So if you want to talk about how to do those, we certainly can. So what I've tried to prove to you next is that geometry is destiny. So we've said that content is geometry and geometry is destiny. And now, is that true? Okay. And it's actually, so there's all this buildup, but it's actually, it's a simple answer to start with at least. But it took the community about 15 years to do it. And what I mean is that it took us about 15 to 20 years to measure the mass density of the universe. And so what we do is we take something like the Hubble Ultra Deep Field, and we count all of the galaxies in it. And given that we know what the mass of a galaxy is, we can measure how much mass is actually in the universe, and so we can measure its density. And to that end, we found that the matter density is less than 1. And so by counting the mass in the universe, by only doing that measurement, we would find that the universe indeed ends with a whimper. But the only problem with this is that it's not the full story. So we can ask, we've measured the matter density of the universe, but we can also measure the topology of the universe directly. Okay, and how do we do that? Well, we look at the very first moments of the universe, at least the ones that we can see. So this is the cosmic microwave background, the full sky echo of the Big Bang. And what you're seeing here is the temperature map, or so the density map of the very early universe, where these fluctuations are about 10 to the minus 5, or so I guess it's about 10 to the minus 3, about 1,000 to 10,000 times less than what you pay in taxes on your income. So we see this light, this very, very old light from the entire sky, and what we can learn from it is from really the average size of these small patches. So these red and blue patches we can look at, and we can learn what the shape of the universe is. And how do we do that? Well, the idea is that we know that this is we know from astrophysical arguments and from other observations that this is the matter-photon soup at the time. We know the astrophysics going on here, and so we know what the size of these little patches should be. And then we can observe the size of those patches, and we can try to corroborate between what we observe and what we predict for those sizes. And what do I mean by this? So let's take patches as we would predict them to be in a closed universe. So just like in a closed universe, the angles in the triangle add up to more than 180 degrees. The light will appear to come from a larger angle, and so these patches will appear to be larger. Okay. In a flat universe, there would be basically no disturbance or no deviation from a given size, from given size of the patch. And in an open topology, the angle appears smaller, and so the patches appear smaller. And what we've learned from this, in fact, is that the universe is flat. Actually, I feel like I sound like the Spaniards in the 1400s, right? So hopefully I'm not wrong. But how does this impact the fate of our universe? Well, it tells us that geometry is in fact not destiny. It tells us that just because the shape of our universe, well, I guess that's not the only point here. Let me take a little step back. If you corroborate that with measurements of supernovae and some other work, you find that to fill in between the matter density and that number 1, that total energy density, you need something else. You need something much stranger. You need what has been found to be a dark energy and an unbalancing of the force, Luke. And so we find that geometry is not destiny, but content is destiny. Content is destiny. So there's matter and there's this other stuff. that we have no idea what it is. Some much stranger stuff. But we know that the universe is flat from that very precise topological measurement to within 0.5%. And if you want to know more about dark energy specifically, then I suggest you check out Dragan's talk from a few years ago. It's an excellent talk. So I guess just maybe a little bit of homework if you're curious about extending this and thinking about because it's a little weird, right? It's a little strange. The strangeness for me really comes out if I ask, what happens if the matter density were to be 1 but dark energy were 0? What happens if the universe, if we thought from the original galaxy measurements that the universe were to curve back on itself, but then we also discovered dark energy? What would the expansion of the universe look like then? So that, I'm not sure if that's an afternoon in the pub or a few afternoons. So hopefully I've shown that geometry is not critical to understanding the density or the destiny of the universe, but that the content is. So what's inside us, what's inside our universe is what will govern our fate. Now this concept will pop back up later, probably in about 20 minutes. So I'll just ask you to sit with it and try to marinate with it for a little bit. And now we've counted all the stuff in the universe. We've measured all the mass. Now I want to ask, what does it look like? What's its shape? What are the structures that live inside of our universe? I want to return to this for a moment because this will tell us how those structures that we see today, those galaxy distributions, how they were actually seeded, how they began. Let me step back real quick. So this matter-photon soup, it's called a matter-photon soup because it's so hot that the photons, right before we saw this, photons could not escape this fluid. That means that every fraction of a second, a photon is running into an atom, running into another atom, or a subatomic part of an atom, running into the next one. So you could not see it. And so this is, if you were there, this is what it would look like, right? Completely black, completely opaque. But then as the universe expanded and the universe cooled, it's a little psychedelic, sorry. So as the universe expanded and cooled, essentially the color of the universe changed, and from that hot photon matter soup, condensed particles, just like on water on your window, not just like, but in a way. So with expansion came cooling and particle creation. And what kind of particles am I talking about? Well, your run-of-the-mill, everything that we're made of. This guy was kind of hard to find, but I'm glad I found him. And all of this stuff goes into making what we see in cosmology studies. And basically it's these beautiful galaxy distributions. And this is what I want to get at next, about what are these structures and how did they come to look, how they look to us today. This is from the Great Sloan Digital Sky Survey. So in brief, how do we get from here to here? How do we get from the echo of the Big Bang to the modern collection of mass in the universe? Now to do that, let's take a quick look. There are actually just a few key points that we need to think about. Let's take a quick look at the hot spots in the CMB. These are the places where the matter had been seeded as being more densely organized. They were randomly placed, and they happen to live in these hotspots, these compressed places, these places where there's more matter in the matter-photon soup, higher regions of higher density. And these are the things that became these overdensities in the galaxy distribution. These are the things that became the galaxies. And it's pretty much, structural formation 101 is pretty much a two-step process. This two-step process begins with this randomly distributed set of masses living in unstable equilibrium. So this ball sitting on top of a hill, getting ready to fall. And once it's perturbed, and it and all the other balls and all the other hills around it have no choice but to congregate together in the troughs and the valleys between them. And so after the CMB photons decoupled from the matter, after the light broke out, gravity only had to act and allow the matter to come together. So let's see that in action. So if you look at a simulation of matter in the universe, its size about 43, I think that should be 4.3 million light years. Thanks, man. And then I just want you to pay attention to the how things started off at the, there's going to be a grid line, or it looks like a grid line here, and things are slightly perturbed from it. That's very important. And we see structure form. So matter sitting at these grid lines, but slightly perturbed in this unstable equilibrium, and then gravity acting on them. And so simply, the initial density perturbations of the universe were set by the time of the CMB. And then gravity just had to do its thing to dramatically enhance those perturbations to a much larger density than we had in the past. And so I guess what I'm getting at is that essentially the rich get rich and the poor get poorer. The denser spots get denser and the voids get poorer. These are just so beautiful. I think I just want to look at them again. But I want you to see the structure as it forms. So as this goes, it's going to point out some of the main features the terminology that we actually use when we talk about these. So there are walls of matter, which then condense into filaments, into noodles, and then these filaments are linked. They connect at nodes, which end up being clusters of galaxies. And so that you can see the full three-dimensional structure, let's take another look. Just awesome. Okay. So that's how we get from the seeds, the initial minor overdensities in this hot soup in the early universe, to the structure that we see today. But how do we know this is true? How do we know how all this works? We don't have multiple universes to experiment with. We can't do any controlled experiments, but we can do something quite extraordinary. And this is part of what I'll talk about next week also in a little bit more detail, but we can use simulations. We can use computer simulations to create those grids, putting masses on the grids, perturb the grid, and then let gravity act and solve the equations of motion. We can do that over and over again for essentially 13.7 billion years. And that gives us something to play with. And what we've done, what we've seen is that we can, the picture that I showed of the galaxy distribution from the Sloan Digital Sky Survey, we essentially can recreate that. Not exactly, we're not going to get the same structures that you see in the observations, but statistically, you get the same structures, same sizes. And this is crucial to our work and to that of other fields, right? The ability to simulate when you don't have controlled experiments to do. So what we saw before was a 4.3 million light year scale simulation. That's something that's, how big is that? Let's see, a few references here. Alpha Centauri is a few light years away, right? The size of our universe, however, is much more than this simulation, but this is the largest simulation to date, which is about 1.5 billion light years on a side. And so we saw structure form on a very, very small scale. Now I want to show you a little bit about how the structure condenses on larger scales. And so you see those filaments really coming together, and then you can see the nodes here. And these are our galaxy clusters. And we are a really, really, really tiny piece of that. And I'll show you closer. So let's zoom in on one of these structures. Oh, and just to note, everything that we've done so far on these larger scales is actually quite simple. And a lot of the equations that we can actually solve them by hand analytically, even though it would take a really long time. We use computers to do it. But when we go to scales that are this size, when we look here, the equations get much more complicated. And so if this was our local universe, if this is our local group of galaxies, then we would be a really tiny speck right around there. So next week I'll go into the difference a little bit between the simple structure formation and the nonlinear structure formation that you need to understand things at much smaller scales. Now, if content is our destiny, content tells us what our destiny is, and not geometry, then I want to look at a region similar to similar in size to the regions that we've been looking at just recently. And I want to see what happens to one of these regions far into the future. So what is the fate of our local patch of the universe, at least statistically speaking? So what you're going to see here is a simulation similar to the ones that we've seen, but flown into the future many, many, many billions of years. This was done by a graduate student several years ago here at Michigan. And what you're going to see is that it looks like you're zooming in, but what it really is, it encapsulates the expansion of space. So space is flying out. And just one other caveat, this simulation includes parameters of the universe similar to what we actually have. So this includes the dark energy and the matter and the fractions that we think they exist. Okay. So you can see the particles flying out because space is carrying them away, even though they would like to gravitate toward this big object, but space is running away so fast that it's carrying it away. Okay. And we see an island universe. We see a seemingly lonely universe. And so what you just saw here is that everything that is in our observable universe has either come toward the center of this thing or flown far away. So eventually, this mega galaxy will be the only thing that we'll be able to see in the universe. So if you have any questions about why we're funding astronomy now, it's because in a trillion years, we won't be able to see anything. So the content of our universe has extraordinary and complexly evolving structure. And this arises from initial perturbations and instabilities that are then amplified through gravity. I just want to touch on just for a second, because I think it's topical. How do we know this? So given that we don't have, given there's only one universe, how do we know that what we're measuring makes any sense? And with only information from the past, essentially with just old light, with no controls, how do we know, how can we perform the stereotypical experiment? Now, and I think part of the reality here that we need to face is that data and models go hand in hand. So first, think of scope. Newton was right. Newton was never wrong. We just had to refine what he did, and that's what Einstein did. So when it comes to GPS, when it comes to Mercury's orbit, that works while Newton's doesn't work. But Newton's ideas work at other scales. And knowledge is more than just pure data, right? It's these simulations that embody our models are the things that will enable us to make future breakthroughs. And this is one of the other key points in my talk next week, and so I'm not going to spoil it for you, but here's another piece of homework. What science fields share cosmology's challenges in this way? So the last thing I want to talk about, this is actually going a lot faster than wow, it's a lot faster. Last thing I want to talk about is the shape of scientific collaboration. How is science collaboration evolving? I don't know if anyone knows the Ant-Man, but E.O. Wilson figured out how ants communicate with each other. And this is what scientists do. This is how science has worked for centuries. We go into our little holes and we figure something out, and then we come back out and try to help each other understand it and help many people understand it. E.O. Wilson thinks that the future of knowledge is actually held in this thing called term that he coined consilience. It's that these narrow channels that have been dug inside the anthills will eventually reconverge, even from art to science and from math to other fields, to literature, et cetera. And so what bearing does this have for us today as our collaborations, as our scientific collaborations grow and scale, and as the size of the data samples that we're gathering from the sky and from nature also grow? So Donald Glaser used to work here at Michigan. He earned the Nobel Prize, and he was also the inventor of the bubble chamber, which is what we see here. I don't think he bathed in that, but and so tabletop discoveries could get you really far in the past. You could do breakthrough science on the tabletop, just like discovering the trajectories of charged particles in these bubble chambers. But unless you're Tony Stark, you're probably not going to build a major particle accelerator today, at least not by yourself. Today, we need megabytes per second of data. Actually, that's 15 years ago. But Fermilab was really successful at finding the top, not just because of the power of their instruments, but because of the power of their collaboration. Because they were able to gather together hundreds of scientists, thousands of scientists, like herding cats. They were able to gather them together and learn from each other and collaborate. The LHC is an even bigger problem. More scientists, more data. Astronomy is not immune from this. Hubble had some assistance, but he worked on the data a lot by himself. He was able to forage on his own path, but in the future, the Dark Energy Survey will take terabytes of data per night. And after that, in 15 years, 20 years, maybe the Large Synoptic Survey Telescope will take petabytes per week. Petabyte is orders of magnitude more than a terabyte. So I think what we're emerging into is the super collaborative era. So I don't know, I used to do SETI at home. I don't know if any of you guys did this. I tried to set up a couple of computers to do it, but basically it would automatically download data and you thought you were gonna find ET, right? You thought you were gonna help do that. Maybe somebody still will. That would be great. And Galaxy Zoo has actually published papers with some of the longest author lists ever because they found that people will spend hours and hours and hours, and these aren't just graduate students who want to procrastinate. They'll spend hours and hours and hours helping classify the shapes of galaxies. Okay. And Rosetta at Home is good for probing the genome. But so what are the next steps? So these projects all just use your basic ability to see a shape and click, see a shape and click, or let your computer do all the work. What is the next step? How do we take ourselves beyond robots, right? One idea lies here in the idea, or in this article in the LA Times last year, where some gamers were actually just able to solve a genomics problem faster than scientists were because it was put into a game form. So if we're going to involve everyone in science in the future, given the scarce resources, if we're going to involve everyone, are we going to be able to, how are we really going to use everyone's skills? How are we really going to engage everyone so that we can be more than foraging ants? And so my last question to you is, and this is something I haven't figured out yet. I think this is part of the future of science. This is part of the crux. What will we do in this next era to engage all the learners? Yeah, like I said, it actually went much shorter than I planned. I think I forgot to do a demo, so I'm actually finished. Thank you.
Do you want to do the demo?
Sure, let's do one of these demos.
Let's go ahead and turn off the lights and look at the demo before we go, and then we'll have some Q&A.
Okay. So remember gravitational instability. right? It's similar to what we saw in the video, and this is sort of a work in progress, but I thought it was really fun as long as I don't mess it up. So, oh, thanks. So these are these random density fluctuations in the universe. And if I can grab them, we'll watch the balls make their choices as they go from one point to the next. So remember, another key point is that this is all happening while space is expanding. So there's this really interesting tug of war between the expansion, actually sort of a three-way tug of war, between the expansion of space, the shape of space, if it were there. Who said no? And the matter in the universe that's pulling everything back together. Okay. The other demo, actually, I guess we could do it. Yeah, let's do it. Let me turn this guy on. So this was just to, let's see. This is just to emphasize how the patches in the early universe and how the shape of the universe changes the size of those patches. So, so I'm not sure if you can see this, but what we're gonna see is that the universe sort of acts like a lens, right? And this is what gravitational lensing does. The universe acts like a lens, and so it will take a shape and change the size of it. So you can see these light rays being bent, and this is what space-time does to light if it's shaped. So that was a convex lens that would decrease the size of the patches, sorry, and this would increase the size of the patches. So this would be the closed universe. Okay. Thanks.
Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.